Oh, there we go.
Okay.
Good morning, guys. Welcome to our SNIA webcast. Is the data really gone? A primer on the sanitization of storage devices. So here with me, I have two experts on media sanitization, my friends from NVM Express and IEEE. We've been working on a new specification for media sanitization called P2883, which we're going to go through, and a lot more details on media sanitization and why it's important. So myself, I'm John Michael Hans from Chia Network. And I was part of the SNIA Computational Storage Working Group and SSD Working Group. I used to co-chair the SSD Working Group. And here with me is Jim Hatfield and John Geldman. If you guys want to quickly introduce yourself.
I'm also the chair of the IEEE Security and Storage Work Group, where a lot of this work is being done.
Hi, I'm John Geldman, and I am also, in addition to being a SNIA board member, I'm also an NVMe board member and a co-chair of one of those committees. And I'm probably responsible for the concept of a sanitization command and integrating it in many of our fine interfaces.
Yeah, John wrote quite a bit of the NVMe spec in this area. So if you guys have some questions at the end, we have the right folks on the call.
For what it's worth, actually, it started with ATA and SCSI and compact flash, believe it or not.
Yeah,
another story.
I love it. I remember sending my very first ATA security erase unit. Yeah, I had to manually construct the command in some obscure C++ code to send the command. But yes, it's the concept has been around for a while. But as you'll see today, the technology has matured quite a bit. So here's our final slide on SNIA and CSMI, the compute storage work group. Today we're going to kind of go, it's kind of around SSDs and hard drives, but really we wanted to focus on media sanitization as it pertains to storage devices. So what we're going to talk about, I'm going to quickly give a primer on sustainability and media sanitization. I am one of the co-authors of the new IEEE P2883, but my contribution is very small in this sustainability section and reviewing it. But we're going to describe what sanitization is, and then Jim is going to walk us through the actual new standards. IEEE P2883 is the new best-in-class media sanitization specification. It's an international spec, and it's we're going to be talking about it quite a bit because it's going to be very impactful, especially in my area where I focus quite a bit now on sustainability. And John is going to talk us through the verification and validation of sanitization and how one does that. And then I'm going to give a quick example of how to actually send an NVMe sanitize command on an SSD. So with that, switch over here. Okay. Let's see. Let me mute you, John, real quick. There we go. Doesn't like switching now, so I'm just going to leave it here. All right. So yeah, the unfortunate, this is a quote from this GRIST article about, the article is titled, "Can you recycle a hard drive? Google is quietly trying to find out." And the quote basically just says, typically when a data center operator swaps out old drives for new ones, as they do every 3 to 5 years, the discarded drives are unceremoniously shredded. Now, this is a really big problem. So why are hyperscalers just swapping out drives every 3 years to 5 years? Well, they do so when the TCO is advantageous for them. And now these guys have huge growing data demands. So their TCO at hyperscale looks a lot different than somebody running a small data center. And some drives that may look old to a hyperscaler, like right now, 12 terabyte drives and 14 terabyte drives are kind of being phased out for these newer 18 and 20 terabyte drives. Those old drives are perfectly fine for a huge class of people. Now, unfortunately, these drives get shredded because of a risk of perception of data leaking. And whoever the policymakers are, you'll see there's some old standards that basically say, if data is leaving organizational control, then the most secure way is to actually destruct and physically destroy the device. You'll hopefully learn today that the old method of shredding a hard drive, actually, the funniest thing about this is that track density on hard disk drives have gotten so dense that even shredding now is not adequate for protecting doing a proper media sanitization. You'll see that these little tiny shreds of hard drives actually contain a large amount of data. So, but policymakers, they just think, oh, shredding equals secure, and thus it must work. So you'll see after this presentation, this is not such a good idea. And so one of the things I focus on from Chia Network, and I'm part of the OCP sustainability work group for storage. And one of the main things we're highlighting on is the circular economy for storage. We are in the process of authoring a extensive white paper on this topic, and media sanitization is actually a huge part. So the way the circular economy works is today, after you use the drive, you want to extend the use phase as long as possible. You do that with features and making drives very reliable and features that keep the drive running. And so today I mentioned that 3 to 5 years. Well, that easily could be 5 to 7 years. And we actually are seeing that for SSDs. Some hyperscalers are moving to a longer use phase, especially for SSDs compared to hard drives. But then the most important part is after the end of first use, you want to be able to properly sanitize it. And we'll learn today a sanitized purge method leaves the device in one piece instead of destroying it. And then you verify the sanitization, and then you can actually sell that device to another party for second use. And now you get, not only do you get value recovery of the components, you get to sell the drive and you get money back. That's great. But you also save a tremendous amount of carbon impact. Hard drives and SSDs have very different carbon life cycle assessment and greenhouse gas emission profiles. I mean, hard drives take a little bit more of the use phase because some of them happen to be higher power than SSDs. SSDs tend to take a tremendous amount of water and energy during manufacturing phase. The NAND fabs consume a tremendous amount of electricity and water. So this is a huge deal. When you actually reuse the device instead of destroying it, you actually get to reduce the scope 3 emissions of that associated drive for the manufacturing phase. So this has a huge carbon impact for being able to use the drive a second time. Now, in a proper circular economy, once the drive cannot be used anymore, you break it down into recover the components. Now, in a hard drive, this might be the magnet assemblies, or on an SSD, it might be the actual NAND die itself, if the NAND die are okay, or some of the components. And if you can recover those and still be used as components, that is much better than just destroying them. And even the recover phase generally is about 7 to 8 times worse as far as carbon impact versus a second use. And then recycling is really when you start breaking these down into raw materials. And so in the hard drive world, that might look like an actual magnet, not the magnet assembly, but just the magnet itself and the really raw components. The problem is now, if you just shred the drives, they get broken. You go right from use phase all the way to resources. So you're basically skipping any opportunity for second use. You're skipping any opportunity for recovering components. You're skipping any opportunity to recycle. You're basically going right to resources. Now, unfortunately, with the hard drive, you have these rare earth magnets, you have the aluminum, they're all mixed together. It makes this tremendously hard to do value recovery. They can't sort through all this material effectively in a cost-effective way. So it actually happens to be 300 times worse than a second use as far as carbon impact. But even then, you go back into industry production infrastructure and you try to get those materials back into the use for a new drive. But if done properly, you should see the use phase and second use phase be the majority of the use, and value recovery for hard drives and SSDs. So as you'll see, sanitize is an absolutely key component to making this happen. So I took this picture from Adobe. I was looking for some stock photos for this presentation, and I just typed in hard drive destroy, and this is what it shows up. And Gemini's favorite is this this one with the eraser here on the drive. That is in fact not an approved sanitization method, as well as drilling and smashing and hammering. These are all not approved media sanitization methods. They may feel good and look awesome, but unfortunately, sanitization is not related to FIPS. It's not just deleting files. It's not trim. It's not these fuzzy industry terms like data deletion, data clearing, data erasure, destruction, wiping. If you go to some of these ITAD companies' websites, they have these, we support 15 different DoD overwrite patterns. And so these things that used to be a big deal and are deprecated now, it's really confusing. Blindly degaussing, shredding, pulverizing. Again, these are not media sanitization. This is just destruction, and it's not a proper way to do media sanitization. So what is media sanitization? Sanitization is a process or method to render access to target data on storage media infeasible for a given level of effort. Now, this is very important. We'll talk about some sanitization methods and techniques, but the really important part is that with state-of-the-art equipment, we want to make it infeasible to recover data. Now, obviously, there are people that are going to say, well, what about 10 years in the future? What about quantum computing? What about all this stuff? So there are ways around all that. We'll talk through some of these approved sanitization methods, but there's always going to be somebody that can spend billions of dollars to try to recover the data. But contrast this with people that are actually making the physics and engineering of these devices. They'll tell you it is very challenging and very hard to recover the data, if not outright impossible in some cases. So today we're going to spend most of the time on a new international standard called IEEE P2883. And as we mentioned, the IEEE work group for security and storage has been working on this new sanitization specification, which defines sanitization. It defines sanitization methods and techniques for specific media types. So for hard drives, for SSD, for optical, removable. And then it defines specific interface techniques for SATA, SAS, and NVMe, most notably the sanitize command, which we will talk about extensively today. And the most important part is aligning the industry and terminology on modern techniques for media sanitization. So as we just talked about, there's a lot of terms thrown around in this industry. I spent a lot of time with these companies and even looked at their websites. And unfortunately, a lot of people are still referencing the NIST 888, which was a lot of guidance. A lot of people are referencing old specifications. A lot of people are just claiming that they have superior third-party software that does media sanitization. So what we'll do is define some ways to actually do this with things that are mostly built into the drive. But the important part of media sanitization, it does target all logical and physical locations for data. So this not only means old user data, but it can be metadata, over provisioning, spare area, places that you wouldn't expect user data, or for common ways to include. So the ones we're going to talk about mostly today are these three sanitization methods. Now, within these methods, there are different techniques to do in commands. We mentioned on specific protocols and interfaces, but these are the three methods that are defined in the P2883 specification. So the big thing about clear is it uses logical techniques to remove all the data on addressable storage, and it's just ideally it's just to prevent non-invasive data recovery. So if you're formatting a drive or deallocating, sometimes on a file system. If you do a format, it just changes the file system and it's going to leave the data intact. Well, a clear may actually do a simple overwrite, but not to spare area. Jim's going to talk through all these actual clear methods. But the most important today we're going to talk about, especially as it pertains to the circular economy and reuse, is purge media sanitization. So purge uses logical or physical techniques to remove all data, and it makes it infeasible data recovery with state-of-the-art equipment. And so this is really important, that even if you are prying NAND off a drive and trying to put them in a tester and trying to decrypt the data with state-of-the-art equipment, the idea of a purge is that you can prevent against all these state-of-the-art equipment, and it leaves the drive in a usable state, which is the most important thing that we need for value recovery and reuse in the circular economy. So we're going to talk through three methods to do a purge sanitization, which are block erase, crypto erase, and overwrite. And we'll talk about which one of these work on hard drives and which one work on SSDs. And then destruct. There is actually new methods for destruct. I mentioned the example before, which was shredding is now actually deprecated because it is in fact not safe as a way to destroy drives. But destruct is a method that you need when drives fail or you can't access the media or the drive won't power on or something. You do need the destruct method in some cases, and we'll talk about what the state-of-the-art methods for destruction are. So with that, I'm going to hand it over to Jim and take it away.
So talk about sanitization. And so the scope for purge and destruct is everything that is, was, or could be user data, and also hints about user data. For example, if you have an error log that says LBA 45 through 100, where you had an error at one point, that could give you a clue as to where to look in a 50 terabyte hard drive. Instead of looking through the whole thing, the error log and other logs like that can tell you where things were actually used. So we sanitize those hints as well. We talked about state-of-the-art laboratory techniques. This includes disassembly and spin stands, electron microscopy, X-ray probing, decapping a chip, and a lot of things that are really expensive. That if you really want it, you'll try and do it. So the sanitization process, we talked about clear, purge, and destruct. We got this little flow chart here so that if you start at clear, for example, you decide you're going to start with a clear technique, you perform it, then as a result of this clear, this includes the verification step. If the clear was successful and the verification was good, you can just go straight to documenting your sanitization results and call it good. Otherwise, you can retry it. For example, say you were in the middle of formatting a 100 petabyte hard drive or SSD, and you had a power cycle. Well, you may need to, oh, slides disappeared. You may need to start it over again. So that's what the retry allows you to do. But at some point, if you decide you're done retrying, you can fall through to purge and do a more secure form of sanitization. Again, you do the purge and the verification. If it was successful and the verification was successful, then you document your results and move on. But maybe your storage device just won't even power up. Well, in that case, you can't do a clear or a purge, and you'll have to go down to destruct. You do the destruct and the verification, and then you document your results and you move on. So we'll see these symbols of clear, purge, and destruct on the following slides. So there's a lot of factors that affect your ability to sanitize. Maybe you don't know what kind of media you have. Maybe you don't know what kind of interface you have. As an example, there's a lot of different kinds of tape cartridges, and you may not be able to tell from the label, which may have been scraped off, what kind of technology is inside. If you have say a hard drive that's got a USB cable on it, you don't know what's really inside that enclosure unless you open it up. Laptops, they're a lot harder to open up than a USB enclosure, and certainly mobile devices are even harder. Furthermore, storage devices may be embedded in chips that you are not accessible. It may be that you don't have the expertise or the tools to sanitize things. You might not be able to have a computer that can execute the sanitize command. Maybe your storage device is not working, or your test equipment is not working. Maybe you've got a shredder and your shredder's not working. All of these factors go into choosing which sanitization technique you want to use or need to use. Most importantly, though, your organization may dictate which sanitization method you use. As John Michael said, some organizations, their security policy is you shall destruct. We're hoping to change that in the near future, but your organizational policy is a very important thing. So we talked about overwrite. There's the word overwrite has many meanings. So we've made a distinction between simple overwrite for the clear sanitization method. That's just writing a pattern or deallocating whatever like logical blocks are accessible through the host interface. So you might be able to write to every logical block on the device, or format it, or security erase unit. You may unmap or deallocate or trim all of the logical blocks. But if you do a trim, you're not going to be changing any of the data that's underneath that was there before. You're just removing host access to it, so that if somebody took the device apart, they could still get the data. Now, sanitize overwrite is a purge technique, and we write in a sanitize overwrite. A pattern is written to all logical and physical locations within the scope of sanitize. The IEEE 2883 document clearly identifies what is in the scope of sanitize, and each of the interfaces, NVMe, SAS, and SATA, they define what's within the scope of their individual sanitize commands. But basically speaking, it's everything that is user data, was user data, like things that have been deallocated or reallocated, or they've been where leveled. You wrote to it, but through where leveling, you have one or more old copies of your data. Those have to be written to. And in addition, everything that could be user data. So anything that's over provisioned or has not been written to, that has to be sanitized by overwriting as well. Now, overwrite is not applicable or appropriate for, say, non-magnetic media. No matter how many times you overwrite a piece of paper, there's ways to still get that. I see archaeologists using X-rays and X-ray diffraction techniques to recover data from, say, the Dead Sea Scrolls that have been rolled up for thousands of years, and they can still get the data off of it even without unrolling it. It's also not appropriate for solid state media like NAND flash, because overwriting it negatively affects write amplification and the endurance of the device. So we have a different technique for that.
That's simple overwrite.
Yes, well, the sanitize overwrite as well.
Sanitize overwrite will not affect write amplification. Sorry, I didn't catch that earlier.
Okay. So for SSDs, block erase is a native technique for NAND flash, for example, and it erases the data in a single operation. But you can't use it for magnetic media. And after a block erase, the media may or may not be readable, because CRCs, depending upon the technique, the CRC for the block may also be erased and not recomputed. The media could be typically all binary zeros or all binary ones. And this, of course, reduces the negative effect of write amplification that overwrite would do. So block erase is the preferred technique for solid state media. Then we also have sanitized cryptographic arrays. This is a method that applies if the device is self-encrypting the data that comes from the host. So the data would come from the host in the clear, and then the device would encrypt it as it arrives in the device, store it in an encrypted manner on the media, and then reverse that and decrypt it on the way out. For a self-encrypting device, the media encryption key is stored inside the device and never leaves. To unlock it, the host sends an authentication sequence with a different password. The host never knows the media encryption key, but they can unlock it. So with cryptographic arrays, you can, by replacing the media encryption key with a different media encryption key, you effectively remove all access to the existing data. The existing data on the media is not changed, but because the stored encryption key has been changed, the device is not able to decrypt it as it was before. There's a companion document to the IEEE 2883, which is the ISO IEC 27040, which is the standard for storage security. That standard has been rewritten, and a new revision is pending and coming out in parallel to the 2883 document. And it previously talked about, and 2883 now talks about, there are preconditions for a proper cryptographic erase. So you need, before you choose cryptographic erase as your method, it's important that you determine for yourself and your security policy that the cryptographic erase by the vendor is appropriate and proper for your needs. I'll also point out that we're just talking about media-based sanitization here. Sanitization of data in the cloud is not covered. Data in transit is not covered. This is just data at rest. Some more things that to consider when talking about cryptographic erase. It can be executed in seconds. If you've got a high capacity, say a 20 or 30 terabyte hard drive, it could take days, several days to do a proper overwrite. And if you have a repetition count in there, it could take weeks to sanitize it. Cryptographic erase can be executed in seconds. And some people, some organizations who own the storage do a cryptographic erase and an overwrite or a block erase. But that's up to their security policy. John Michael talked about Destruct. Some of the techniques that were previously in the ISO IEC 27040 are melting and incineration. Here's the definitions of what melting and incineration are. But these techniques are not environmentally friendly. So there are problems with that. There's problems with all of the destruct methods. Shredding and pulverizing have been obsoleted. As an example, if you have, say, like a 2mm by 2mm shredded particle from a hard drive, that given the enormous densities on the recording surface, that could actually contain hundreds of thousands of uh, paper page, hundreds of thousands of paper equivalents of data. So these methods have been obsoleted. Okay. That's it for the description of sanitization. Oh, I do need to mention the IEEE 2883 standard will be published and available in a couple of months. And with that, I introduce John Geldman, who will talk about verification.
All right. So, unfortunately, verification of sanitization is a bit complicated. Okay. So let me first give you an overview of what it is I'm going to talk about in these few slides that I'm providing here. First, the physical interface, the NVMe PCIe or whatever transport it's using, or SCSI or SATA, they don't provide observability to all standardized functionality. We cover more than the logs and logical blocks that you can get through the interface. Many devices, and this is not just SSDs, have internal integrity checks, and I'm going to talk more about that. And those are designed so that if there ever is a storage failure, bad data doesn't leave the SSD. That's an important first order effect for a quality storage device. And another interesting characteristic of sanitized, in particular for SSDs, is that we deallocate storage before leaving the sanitized operation. That means that when the data needs to be used again, you don't have to waste another erase cycle to get there from here. And also hiding through the device, whether we're talking about hard disks or SSDs, the media is often used for more than user data purposes. There's firmware, statistics, vendor-specific state, many things are kept on the media, and distinguishing those is difficult. When we talk about verification, we often talk about two different aspects of it. One of them is the implementation correct? And I'll call that validation. And I'm not going to talk about it a lot from here on in. And it generally, that takes some kind of design reviews and potentially disassembly of sacrificial devices to look to see what has actually happened. But then there's what practically can be done by storage providers, verification. And that's going to be the bulk of what I talk about. So going through the details of correctness is very difficult. So physical interface doesn't provide observability to all functionality. Over provisioning is famous in SSDs. It can be 30% of the drive or of the storage. It really helps to increase endurance, improve performance, but there's also over-provisioned areas in hard disks also. In addition, there's a lot of nooks and crannies, the caches and buffers in the data path. Those are not typically accessible through through the interface. So depending on the device to do it is kind of important. Also, many SOCs have internal integrity checks. When we use methods such as crypto erase and block erase, then if you have 0-1 balance encoding, which gets applied during a write operation, or if you have integrity data structures, all of those underlying material is pretty much removed. And now you may not be able to read what's left over. And also, on the other hand, the overwrite sanitize operations actually incorporate those normal encoding and integrity, and those just work. So to avoid wasted write cycles, rather than after the information has been removed by the sanitize operation, one of the original concepts behind the original sanitize commands was that you may string a couple of them together. You may do a quick crypto erase so that data isn't easily, and then you may do a block erase following it, followed by a format. We didn't want to add in a lot of extra wear and tear in time. So, and there's also issues with internal complexity. If you're attempting to validate, you're going to have to determine that data left over on the media is user data and not firmware and logs. And that's part of the science of how that stuff works, or the engineering, I should say. And also, media doesn't contain simple readable text. If you've written Big Gorilla or some other phrase in the device as what we call a canary, it's sometimes not easy to see because it may have been encoded for reliability. It's pretty hard to figure out what's what without firmware context, but that is something which is often shared with a deep reviewer for validation. Now, we have put in some interesting tools into NVM Express. One of them is the no deallocation bit, which was added to the sanitize command. It was a relatively good idea, but it turned out to be difficult and expensive. Supporting it required an additional full write of observable space, and that has time and endurance costs. It also just, if you actually had the ability to look at raw data, you've basically overwritten it, and you can't tell that the original sanitize itself had happened. As an example, if you crypto erased and then overwrote with zeros, there's no way to tell if you actually did the crypto erase. All that's observable is the zeros. In NVMe base revision 2, what in the NVMe community we call the NVMe Express, the NVMe 2.0 family of specifications, we've included some development for bits that report that we don't really support no deallocation in the command. It has the lovely name no deallocation inhibit bit, and that has to do with attempting to be backwards compatible. Also, there's the cost of such operations. If you're going to overwrite a 60 terabyte device, that can take you a really long time, as Jim said, potentially weeks, certainly days. So effectively, that time that goes in, and the device will do that type of operation is lumped under something that we call the media modification after sanitization. So that's another mouthful of a phrase we came up to describe that operation. And what that will do, for what it's worth, is if your crypto erase takes place in second, the following modification may take a day, may take longer. But we're not completely, all is not lost. We're not hopeless here. So sanitize verification. what we're aiming at is to make sure that the device was adequately and effectively sanitized. For clear and purge, you can use the device operation to at least check what you can check through the interface to actually see what's happened. When we're talking about destruct, verification means physical inspection. Device is no longer operational. It may be in grains of sand, as Jim has said, or it might be in some other modes. Some sort of physical inspection is what's needed. When you're checking verification, part of 101, and Jim talked about it a bit, is, and 2740 talks about it a bit, is you want to keep some records of what was done, what technician did it, when was it done, what method was used, and that'll help prove that you've taken responsible practices to dealing with the data that you're entrusted with. For clear methods, IEEE 2883, when it's available in a month or so, is going to tell you that if you have data verification required, then you want to do representative sampling. And I'm going to explain what it is in an upcoming slide. And for purge methods, similarly, you might want to do a full verification. The data is more important. It may be more important to your organization to ensure that it's completely gone. In the cases where the data is not available, such as cryptographic erase, where there's no predictable data available, it may not be possible to look for expected results, but you can look for the absence of data. And we've already talked about Destruct. Okay, representative sampling. So IEEE 2883 has the advice, you choose and you look at least 5% of the addressable space. They would like you to take equal-sized portions of the device, take at least 2 blocks in each one of those portions, and do the random sampling of logical blocks to make sure the original data is there. So some caveats in that, you may be looking for not necessarily the spore, the results of cryptographic erase, or the results of block erase, because they might be unpredictable. You might be looking at deallocation data, which is at least enough to tell you that the original data is no longer available through the interface. So I think that's pretty much it for verification. And with that, I'll turn it back, I think, to John Michael to how you actually can do this.
Yes, thank you. There was one question about clarifying deallocate before leaving sanitize. What does that mean physically? So at least on an SSD, deallocate is the way that is used, the terminology is used for trim in the NVMe Express specifications. So deallocate is basically telling the controller that these LBAs are not containing valid user data anymore. Now on the SSD determining what kind of deallocate they support, whether it's deterministic read zero after trim or others, will actually do either a background operation or fire off the erase blocks. There's a combination of things the SSD controller and firmware can do when it receives the deallocate bit. But the deallocate command is a way for the host to tell the SSD this data, these LBAs are no longer storing valid user data.
If I could add a bit to that. So SSDs and many hard disks have translation tables. When you give them a logical address, which comes over the interface, that doesn't actually point to a specific physical address. You go through the translation layer to find where the media is. What the deallocation does is it wipes out that link. Doesn't remove the data, it wipes out that link, so that you don't know where the data is and you end up getting a memory pattern or some pattern, some predictable pattern, rather than the media contents. That link is lost until that physical media entry is assigned to a new physical address.
Awesome. Thanks, John.
Sure.
All right. So actually performing a sanitize, contrary to some of these, if you just Google like how to do a sanitization, you'll probably see some ads for some of these companies selling their proprietary software that's extremely expensive that does these very secure sanitization methods. Well, turns out Sanitize is pretty easy to do with NVMe CLI and other tools that are completely open source and free. And almost every single NVMe SSD today supports NVMe Sanitize. Uh, NVMe 1.0, 1.1, and 1.2 supported something called NVMe format. And with format, you could do a block erase and a crypto erase. But as we mentioned, Sanitize has functionality beyond just be able to do this. So the Sanitize command was added in NVMe 1.3 to actually formalize this process of media sanitization. And so again, we talked about where a format may just be user data. And Sanitize makes all user data unrecoverable, and all the data that was in the non-volatile memory, in the persistent memory region, in the controller memory buffer, in the cache, the metadata, unallocated space, and over provision space. So Sanitize touches all of them. It is a background operation. So when you send the Sanitize command, it starts off a background operation. The command will tell you it's completed successfully, but you have to go check the log to make sure that it's actually running in the background. And in Sanitize, it's very easy. You just look at the Sanitize capabilities in the identify controller, and you'll be able to see what type of Sanitize the drive supports. Some drives support block erase, some drives support crypto erase, some drives support overwrite. On an SSD, we mentioned it's probably not common to support overwrite because it's bad for endurance. So, on data center SSDs, it's pretty common to see a block erase and a crypto erase. And then the Sanitize log page will actually tell you the estimated time for completion for some of these. As we mentioned before, crypto erase is awesome because not only is it secure, but it completes in just a few seconds. Typically, a block erase can take anywhere from tens of seconds to a couple minutes. So what happens with the block erase is the actual SSD controller is actually using voltage in the erase blocks on the NAND to basically zero out those blocks. So as many of the physicists and people that design NAND, the programming methods have become so complex that actually doing this operation makes the data basically instantly unrecoverable. So, and as we mentioned before, you can chain a couple of these together by doing a crypto erase and a block erase. The probability of recovering data with any state-of-the-art equipment is basically zero if you do this correctly. And the great news is you leave the device in one piece. So the way NVMe Sanitize works, again, you check the Sanitize log page for the status, and then when the Sanitize is done, it will send an asynchronous notification to the host, or you can basically just check the Sanitize log page, which we'll show an example of. The great news is you don't need to spend any money to download the NVMe Express specification. You just go to nvmeexpress.org and click on download the spec. You can see there's lots of different sections on Sanitize. There's even an annex on verification of sanitization written by Mr. John Geldman here. And you can see here in the identify log page, you can basically see there in the Sanitize command, you can basically send a start a block erase, start an overwrite, start a crypto erase. And this maps very closely to what you'll see. So NVMe CLI is, again, free and open source tool that allows you to run any single NVMe command you can possibly think of. Now, unfortunately, with great power becomes great responsibility. You have to kind of sometimes open up the NVMe spec to make sure you're running the commands correctly and sending the right commands. But Sanitize is pretty straightforward. So the first thing you want to run when you look at when you're trying to see if does your device support NVMe Sanitize. So you just type in sudo NVMe, or if you're a super user, you can just type in NVMe identify controller /dev/NVMe, whatever. You can optionally put the namespace on there, but the important one is to this -H. This -H is human readable. And my command here, normally the identify controller is going to dump all the identify controller information. What I'm doing is just finding the sanitize capabilities, and then typing -A5 to list the 5 things after it. And so you'll see here, this drive, Kioxia sent me it's like a 1 terabyte consumer drive. So John, you'll be happy that I tested with this thing. I think it's like an XG5 or XG6 or something. So this drive happens to not support overwrite. It happens to not support crypto erase. So you can see the OX1 here on block erase. So I ran this command, and this consumer drive supports block erase. And so I'm going to run the NVMe Sanitize with action 2, because if you look back at the previous slide, the action 2 was start a block erase sanitization method. And it's going to start this in the background. And now the way I know that it started is I just run the same command with -h, human readable, the sanitize log, and I run it on the same NVMe device, and it will tell me all the information about what the sanitize. So in the sanitize status is going to say sanitize in progress, and the S progress bit is going to parse that information and tell me 61% is when I took the screenshot. So this command on this drive actually happened to only take about 10 seconds. Now, I don't even know if it even took that long. So I had to run this pretty fast to capture this. And then when it completes, you just basically you keep checking the status until you run this command and it says most recent sanitize command completed successfully. So that's it. I mean, free open source software, a handful of commands to basically do the verification. Now, as we mentioned, you have some software to actually do that full representative sampling and verification. That's some stuff we actually have to build into some open source tools, and we definitely want to see some volunteers in the future help do that. But I do think that it's pretty low hanging fruit and easy to do. But so if you're on a SATA SSD, you can do a sanitize through HTParm. If you are on a SAS SSD or hard drive, you can use sgutils sanitize command. So all this stuff is free and open source, and we'll have a guide here. I don't know if we do have a page on SNIA yet on this, but we will in the future if we don't, showing how to perform and sanitize and all these free and open source tools. So now I'm going to do a PSA quickly. If you are an SSD company or SSD vendor listening to this, I did find a couple consumer models in my testing that did not support sanitize. These are pretty new models, but they supported, and when I looked at their Opal and TCG, they supported only vendor unique commands, not these standard NVMe sanitize. So the majority of SSDs, the overwhelming majority of them, 90+% of the ones I tested, NVMe SSDs that are 1.3 and beyond support sanitize. So that's good. But if you think that it is better to do a vendor unique command for this, you are wrong. Please implement NVMe sanitize. It is very important as we see to the circular economy and be able to fully reuse devices and complete a sanitized purge. So with that, that was it. We just wanted to give you guys an example of how we would do an NVMe sanitize. Again, it's super straightforward, free and open source. You don't need any proprietary tools. Hopefully, you guys got a good feel about the different methods. Again, the summary we wanted to talk about was purge media sanitization. So whether you support block erase, crypto erase, or overwrite, whether you're a hard drive or an SSD, you need to support purge. And purge is safe and effective for doing a sanitization. It is secure. It is infeasible with state-of-the-art equipment to recover data after a purge. I mentioned talking to the guys who develop NAND SSD technology and controller firmware. After you swap the cryptographic key and zero out the erase blocks, the probability of getting that data is effectively zero. So, hopefully people can understand that this is a safe way to do a sanitize, and you don't need to resort to physical destruction unless the device is indeed broken. So with that, we do have some time for questions. The first one is, NIST mentions the NVMe format with secure erase setting to 1 for user data and 2 for crypto as a purge method. From what I could gather, sanitize was more of a fallout of the format than anything. Okay. So with NVMe sanitize, would you expect format and data erasure options to be deprecated or move back to a clear?
I'd like to tackle that one.
Sure.
So first of all, one of the reasons that, and the three of us were all involved in the development of IEEE 2883, which is designed as a real specification and not a white paper like NIST 888, which actually doesn't have any requirements in it. 888 is getting a little long in the tooth. It's kind of old. They didn't get a lot of industry development in it. And through the years, we've realized that NVMe format with secure erase doesn't have requirements for some of the things that sanitize covers. So we do consider it to be a clear. Vendors can implement those things which are not required. So if you talk to your vendor, it may turn out to be a capable purge, but you do have to talk to your storage vendors to get their opinion on whether or not it can be relied on as a purge. And that is unfortunately a vendor discussion. it is unlikely that we'll add too much to well, we can't add anything to the devices which are already built in terms of is format with secure array sufficient for a purge. We may add proposals on that in the future for new devices, but that won't affect your older devices and how they're designed. Anything to add to that?
The only thing I can add is that, like you said, I'm going to just reiterate it. The NVMe specs do not have requirements actually for what user data erase or crypto erase does and does not do. They say, here's something you can do, but there's no real requirements for what the scope of those operations are. Sanitize does define the scope very clearly.
Yeah, thanks. And so, yeah, to reiterate, if you have an older drive that doesn't support NVMe Sanitize, you can do a format with a crypto erase and block erase, and those are good. But yeah, for new drives, definitely look for and Sanitize support. And we've been, most every data center drive that's 1.3 and beyond should have support for this. So it's a pretty major feature. So there is
client consumer drives also, as you know.
Yeah, they should. Yeah, like I mentioned, there's some. I'm not going to do some name calling out because I know who they are, but there are a few that are not doing this right. So I'm going to yell at them. All right. So a question. This is really around logical storage. So file system, file level, OS, file system, logical volumes. What can be done at a technical level, and to what degree is beyond monitor arrays can do with too many logical layers. I know we have been talking about in the work group, futures about logical storage, and in the future, there's at the SNIA Security Summit, there was a presentation on key per IO, some of the new features coming where the host may manage some crypto keys. And so, is there something you guys want to comment on, logical storage techniques for media sanitization and how that would work?
Let me take a first stab at it. The logical sanitization is something that is not currently in the scope of either the ISO IEC 27040 or IEEE 2883. It's possible that in a future revision of 2883 that might be covered if the work group gets subject matter experts who can guide us through that. This especially is relevant to cloud storage. What we focused on right now is actual media sanitization, not logical sanitization. As for the regulatory alignment, both the SNIA security twig and IEEE security and storage work group have informed regulatory agencies in the US and the European Union of what we're doing and encouraging them to take advantage of what we've done. And we're waiting on whether they're taking action or not.
I would add in the IEEE security in storage workgroup, we have acknowledged that we intentionally did not cover logical sanitization or in the current spec, and we are working on the process of developing what such a similar spec would be for logical, but we haven't done that work yet. And it's not an authorized project yet either.
Yeah. But yeah, to be clear, one of the main use cases for the sanitization is transfer of ownership. And, generally speaking, that doesn't say there are plenty of people that use encryption, or if you're in a virtual environment and having VMs and they have encryption per namespace or per VM and stuff, all that stuff, is completely separate to sanitization, which is really today we talked about the main use case, which is this transfer of ownership.
Let me add something there that's important. You mentioned namespaces. For NVMe, the scope of sanitization is the entire NVM subsystem.
Correct. Awesome. So that was a good answer. Somebody asked a pretty easy question: is over provisioning part of spare blocks, or is it separate? So a NAND page has extra actual extra bytes for ECC, and then an SSD may contain spare blocks, but not just for when there are errors or bad blocks. The spare area is actually used for garbage collection, as well as spare blocks for when the device gets closer to the end of life and the SSD firmware has to start retiring blocks. So yes, or generally almost every SSD has some amount of over provisioning because they don't function without them. Because of course with NAND you have to erase the blocks before you write them. So that is one very, very important part of how SSDs function.
And basically the same thing applies to hard drives too, even NVMe hard drives. You have some over provisioning as part of your reallocation and your reallocation schemes.
So somebody asked a question, which is, full verification is very expensive, especially when you're doing lots of drives. Why can't you do a seed like you could for crypto and verify the seedling is gone and then do some representative sampling? I've actually thought about this a little bit about, obviously I work at Chia and we do proofs of space. We literally invented a way to prove you're storing a certain amount of data on a drive with a mathematical proof, being able to do a quick and easy verification of that. So I've certainly been thinking about how we could use some of that same technology for verification of sanitization. So.
Well, I'll add that in the current IEEE 2883, it recommends full verification after purge. It does not require full verification. You are free to do representative sampling if you choose. That is according to whatever your own security policy is. Your security policy should say which one you're going to do.
Yes, and we mentioned with the background is, after surveying lots of hyperscalers and ITAC companies, we do believe the majority of devices are being destroyed today, which is very sad and frustrating. So the full verification is kind of a way we can say, if you do the verification, you read the data back, and it is indeed the expected outcome that your verification sanitization completed, then that should help with the liability that some large customers and cloud data centers basically have as far as like liability of risk and data for the companies. So with that, I do believe this was the last question. So I'm going to mark that answered. And if you guys have any questions, we will do a follow-up blog on SNIA. I mentioned in that blog, I can add some links of how to do this in HDPARM and SGUtils and NVMe CLI. It's pretty straightforward. And again, thank you, John and Jim, for the talk today. Again, it's been great to work on this specification. And we forgot the biggest news, which is specification has been approved by IEEE, and so there'll be publication here shortly, I believe. I don't know what shortly means, maybe a month or two. But
John Michael, thank you for helping organizing this and pulling us into it. Appreciate it.
Thank you. And I'll add a shameless plug. Please join the SNIA security twig and or the IEEE security and storage working group. If you want details, you can contact us.
With that, thank you guys all and have a wonderful rest of the week. Bye-bye.
Thank you.